Hello, students, and welcome to our lesson on real numbers. Now, the title is real numbers, but what we're actually going to be focusing on is mostly rational numbers. We will talk about how this ties into real numbers and how all the different number types make up the group of real numbers. But most of this lesson is actually going to be focused on rational numbers specifically. So let's go ahead and get into it and see what these definitions are. So first thing we have is that a rational number is any number that can be written as a quotient of two integers. And generally we denote that quotient as P over Q. Now, because rational numbers are numbers that can be written as a quotient, their symbol is a Q. Now, in general, when we write these math symbols to represent big groups, we actually make them much fancier. So usually I would write a fancy Q with an extra line down the side there. But for sake of simplicity, we're just going to use a capital Q because depending on what font you use on, let's say, a computer, it's going to put this symbol in there differently anyway. So we're going to use capital Q. All right, so now a rational number is any quotient of two integers. So you might be thinking of a couple already, like 1 over 3 is an integer over an integer, but also think of whole numbers like the number 2 is actually just the number 2 over 1. So any whole number or any integer is going to work for this because you can just write it over 1. But then also any fraction in general where we have an integer on top and an integer on bottom meets this description. So now as decimals is what this lesson will mostly focus on. Rational numbers include integers, as we just saw. 2 is really 2 over 1, so that meets the description of a quotient of two integers. But it's also going to include decimal expansions that are either terminating decimals, terminating, or they are repeating decimals. So both of those will count, where a terminating decimal is one we see quite often, like 1/4 is equal to 0.25, and it stops. Once you get to that 5, the decimal is over. There's nothing that comes after, so we say it terminates. Okay, but a repeating decimal, such as 1/3, if you type it into a calculator, is going to be 0.33333, and those threes are going to keep going. So we would represent that as a 0.3, where we put a bar over that 3 to represent that it keeps repeating. Okay, and again, this lesson is largely going to be focused on how to turn those decimals back into rational numbers, or into fractions, I should say. All right, so we have rational numbers are quotients of integers, but they might also look like either integers themselves or terminating or repeating decimals. So now an irrational number is quite literally just a number that is not rational. So the whole number system is divided into two groups. We either have rational or we have irrational, where rational we just described, and then everything else is irrational. Irrational numbers will have non-terminating and non-repeating decimal expansions. And some common examples of this are pi, which the symbol is right there, 2 lines down with a little hat, or Euler's number, which is the letter E. So if you've ever seen an E on a calculator, it represents a specific number. We call it Euler's number for the guy that named it. And then non-perfect roots, such as the square root of 2, the square root of 7, really the square root of anything that is not a perfect square is going to be an irrational number. And those three are really the only types of irrational numbers you particularly need to be aware of, and we'll reference those quite a few times in here. So now we're going to classify each number below as either rational or irrational, and I showed you the letter Q, that capital Q represents rational, and then the letter I is going to represent irrational, where specifically this needs to be a capital I for irrational. If you write a lowercase I in mathematics, that has a different meaning, which we're not going to dive into here, but that represents an imaginary number. So for irrational, we need that capital I. All right, so now down at number 1. 3 over 5 is 3/5. That is an integer on top and an integer on bottom. And so that is the definition of a rational number. So we're going to put a Q there. -7 is an integer. So by default, it can be written as -7 over 1, which makes it again a rational number. Number 3, 0.125 we already know how to turn terminating decimals into fractions. 0.125 is 125 thousandths. And so notice 125 is an integer and 1000 is an integer. So this represents a rational number. So any terminating decimal is actually easy to see why it's rational because we know how to turn it into a fraction already. Number 4 is 0.27 with a bar over the 27. So this means it's 0.272727, where that 27 keeps going. Okay, we're going to see in this lesson how to turn that into a fraction, but take my word for it for now, that because it repeats, this is a rational number. Number 5 is a perfect root. So square root of 49 equals 7. That is just an integer, so that's rational. And number 6, the square root of 2, if you try to turn that into anything else, it's really not going to work. So this is going to be irrational. And real quick, I just want to show you on the calculator, square root of 2, if you look at the decimals there, 1.41, it starts to feel like there's going to be some repetition because we have 1.414. So you might think, okay, 1414, but then it changes. Then we have 2, 1, 3, 5, 6, 2, and it's never going to actually repeat and it's never going to terminate. Okay, so it's hard to tell when a number is irrational on a calculator because it feels like it terminates since the calculator stops putting more digits. But when you have no clear pattern, that almost always is going to mean that this is an irrational number. And for us, the way we're going to tell is the fact that it's a square root of a non-perfect square. All right, so now we're going to learn how to turn these repeating decimals into fractions. And this is the bulk of the lesson because it's the only thing that requires real work on our part. So now we're going to have two different scenarios here. The first couple problems we're going to do have just a repeating part and nothing else in them. And then the second block of scenarios, we're going to have a repeating part, but also a non-repeating part in front of it. And the process is slightly different depending on what scenario we're in. And to me, this is the most fun thing I get to teach you all year because I don't think very many people know how to do this. And so you guys are now going to be ahead of the game and you're going to be able to convert repeating decimals back into fractions. So let's see the steps. Step 1, let x be the repeating decimal. So whatever decimal we're given, we're just going to call that x. So if you look at number 7, it says 0.6 with a bar over the 6. I'm going to do in step 1, I'm just going to call this x equals 0.6 with a bar over that 6. So step 1 is just name that thing x. Step 2, or part B up there, is identify, and we're going to call this the length k of the repeating block. So we want to know how many characters long is the part under the bar. So down here at 0.6 with a bar over the 6, there's only one digit under that bar. So we're going to say that k equals 1 to represent that 1/6 that's under the bar. Part C says to multiply x by 10 to the power k so that one full repeating block sits immediately to the left of the decimal. So now 10 to the k is the number we just found. It's the length of the block. And so what we're going to do is we're going to multiply x, which is 0.6 with a bar over it, by 10 to the power 1. So down below here, I'm going to do x equals 0. And this time I'm going to write out a bunch of 6's just to represent the fact that those 6's keep going. Okay, so 0.666 with some dots after it. And we are going to multiply this by 10 to the power k, which is 10 to the power 1 because our k value was 1. When I do this step, I'm going to do it right next to it. X times 10 to the power 1 because we have to distribute this 10 here. So x times 10 gives me 10x. And on the other side, 0.66666, where the 6's keep going, times 10, we just have to move the decimal place once to the side. And so this gives me 6 point and then the 6's that keep repeating. And I'm going to go ahead and move this down to over here just because it's going to make our next step a little bit easier. Sorry about that, but just going to write it down below. So we now have 10x equals 6 point, and then those 6's just keep on going for forever. All right, so those are the first 3 steps. Now, part D, we are going to subtract the original equation from this new one to eliminate the repeating decimals. So the equation we just got, and I'm going to write it in red to make it ultra clear what's happening here. We have 10x equals 6.66, where the sixes keep going. That's our new equation from part C. We're going to subtract the original equation. So the original equation was x equals 0. And I'm going to write the sixes with some dots after it, where those sixes keep going. So what part C tells me to do is actually subtract right here. So I'm going to subtract this entire equation from what's above it. So now this is the first time we've done something like this. But the reason we're allowed to subtract like this is because we know that x is equal to this 0 and the sixes keep going. So because we have two things that are equal to each other, we can put minus x on the left and minus 0.66666 on the right because they're the same thing. So we're allowed to do the same thing on both sides of the equation. So now what happens here is on the left side, 10x minus x gives me 9x. And on the right side, the part that repeats, the 0.666, those cancel each other out when we do this subtraction. So we're just left with 6. Okay, so now part E says solve for x and reduce the fraction. So we have 9x equals 6. We're now just going to solve this by dividing both sides by 9 to get x equals 6 over 9. Okay, just dividing both sides of this by 9. And if we reduce that fraction, we get x equals 2 over 3. So what we have just shown is that 0.6, where the 6 repeats, is actually just 2/3. So now watch this on a calculator. If I type in 2 divided by 3, look at that decimal expansion. It's a whole bunch of sixes, and then the 7 that you see at the end is because the calculator rounded that last number that it shows. So 2/3 is 0.6666666, where the sixes go on for forever. All right, so we did that one as we were seeing the steps. Now for part 8, we're going to do it all in one go. And you're going to see it actually doesn't take too long. So step 1 was name our number x. So 0.42, where the bar is over the 42. I'm just going to start by saying x equals 0.42 with that bar over it. But to make this a little bit easier, instead of using the bar, I'm going to write out 2 of the 4 2s and then some dots. Okay, so that means the same thing as the bar. Now, part 2, or step B, says identify the length of the repeating part. Underneath that bar is 2 digits, 4 and 2. So k equals 2 here because there are 2 digits that repeat. Part C says to multiply x by 10 to the power 2 in this case. So I'm going to take x equals 0.4242, where those 4 2's keep going. And I'm going to multiply this entire thing by 10 to the power 2 because k is 2. So that's just 100. I'm going to multiply by 100. When I multiply both sides of this by 100, because remember I have to distribute to both sides, do that in red. On the left side, x times 100 is 100x. And on the right side, 0.4242 times 100, we just move the decimal place twice to the right. So we get 42.42 with a dot, 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 because those 4 2's keep going. Part D says to subtract the original equation. So I'm going to put x equals 0.4242, where those 4 2's keep going underneath. And I'm going to subtract this from what's above it. On the left side, I have 100x minus 1x. That gives me 99x. On the right side, the decimal part, all the 4 2's cancel each other out. And so we're just left with the 42 in front. Okay, so 42.424242 minus 0.424242. Those decimals just cancel out. So we're just left with 42. And now if I divide both sides by 99, we have our solution here that x is equal to 42 over 99. Both those numbers are divisible by 3. This reduces to be 14 over 33. So now, do you believe me that 0.42 repeating is 14 over 33? Let's give it a try. 14 divided by 33. See all those 4 2's? All right, so I do not lie. Let's make this a little bit harder though, because I know you guys are thinking, hey, Mr. K, we can handle more than this. Okay, those ones were pretty easy. Let's make this harder. So let's go ahead and try. Now we're going to be converting mixed, non-repeating and repeating decimals to fractions. So we're going to take it up a notch, and we're going to have 2 of these. So I'm going to do the first one just like I did before, where I'll kind of go step by step as we write the steps. And the second one we'll do all in one go. So step 1, let x be the mixed repeating decimal. So step 1 is the same, just name our number x. So for number 9 here, 0.36, the bar is only over the 6. So this number is x equals 0.3666, and those 6's keep going. Step 2 says to identify the number of non-repeating. Okay, so this is different now. This is the number of non-repeating digits. We're going to call that m, and we're also going to find the number of repeating digits and call that n. So we're going to find 2 things here. For our current number, 0.36 with the bar only over the 6, our m is going to be equal to 1. It's just the number 3. Okay, and our n is also going to be equal to 1, where it's the 6 that repeats. So both m and n are 1 in this case. Now, step C says to multiply x by 10 to the power m, so only the repeating part remains. So let's go ahead and try that real quick. We're going to multiply x, which is x equals 0.3666, with the 6's keep going. We're going to multiply this thing by 10 to the power m, which is 10 to the power 1 in this case. When I do that, I distribute this 10 to both sides, and I get 10x is equal to, I move the decimal place once on the other side, and it's 3 point, and then all these 6's that keep going. So we have one equation now that says 10x equals 3.66666, and the 6's keep going. Now step D says to separately multiply x by 10 to the power m plus n, so that one full repeating block sits to the left of the decimal. So I'm going to do almost the exact same thing here. I'm going to start with x equals 0.3 and then all these 6's. But this time I'm going to multiply by 10 to the power 2. So now why 2? Well, m plus n is equal to 1 plus 1, which is 2. Okay, so we have 2 total for when we add together m and n. So we're going to now distribute this 10 squared, which is 100, to both sides of this equation. That gives us 100x equals, and on the other one, we move the decimal place twice. So we're going to get 36 point, and then all the 6's repeating. Okay, so now we have 2 new equations. 10x equals 3 point, a bunch of 6's, and 100x equals 36 point, a bunch of 6's. Step E now is going to tell us to subtract the 2 equations to eliminate the repeating part. So we are going to subtract the 10x one from the 100x one, and then we're going to solve for x and reduce the fraction. So down here, I have my 2 equations. All I'm going to do is subtract them from each other. So I'm going to take 100x equals 36 point, all these 6's, and I'm going to subtract from it 10x equals 3 point, a bunch of 6's. And when I do this subtraction, it's going to give me an equation that I can solve for the answer. So on the left, 100x minus 10x, that is 90x. And on the right side, the decimals are going to cancel each other out, just like before. And then we just have 36 minus 3, which is 33. So now I solve for x by dividing both sides by 90. And this leaves me with x equals 33 over 90 reduces to be 11 over, if we divide, oh, sorry, not 11. Yeah, 11. We're dividing by 3. So 11 over 30 is what we end up with. So now, do you believe me that 11 over 30 is 0.3 and then a bunch of 6's? Well, let's see. 11 divided by 30. Hey, look at that. 0.3, then all those sixes. All right, so now we're going to do it again with a slightly bigger number. See if we can get a similar result. So this time we'll go all in one go. Number 10. We have 0.16 and then 27 repeating. So I'm going to start by saying x equals this number, 0.16, and I'm going to write 2727, where I'm just going to put two of them to show it repeats. We're going to identify the part that does not repeat, which is this 1 and 6. So we're going to say that m equals 2, because there's two digits that don't repeat. And the 27 is the part that repeats, so n is also going to be 2. And so that means that together, m plus n is going to equal 4. So now we have to find two new equations. We're going to take x equals 0.162727 dot dot dot. And at first, we're going to multiply this like we did before by 10 to the power m. So we're going to multiply this thing by 10 to the power 2, which is 100. When I distribute that 100, I get 100x equals, and if I move the decimal place twice to the right on the other side, 16.2727 dot dot dot. So that's one equation. Now we're going to do it again. We're going to start with x equals 0.162727 dot dot dot. And this time we're going to multiply it by 10, not to the power 2, but to the power 4, because it's m plus n now. So we distribute this 10 to the power 4 to both sides. 10 to the power 4 is 10,000. So I have 10,000x is equal to, and I have to move the decimal 4 spots on the other side. So 1627.27 and then dot dot dot. Okay, we now have two new equations, and now we're going to subtract them from each other. So I'm going to take 10,000x equals 1,627.27, where the two sevens repeat, and I'm going to subtract from that 100x equals 16.2727, where those repeat. And when I do this subtraction, I get the equation that I can solve to get my answer. So 10,000x minus 100x is 9,900x. And on the other side, the decimals cancel each other out. We have 1627 minus 16 is going to be 1611. And now if we divide both sides by 9,900 and we reduce our fraction, we're going to end up with our answer. So we're going to get that x equals, and if we reduce this thing, both top and bottom are divisible by 9. So we're going to end up with 179 over 1100 as our fraction. But if I'm being honest with you, I didn't have to, but I decided to cheat and use the calculator to get that reduction. So the way we can do that is 1611 divided by 9900, turn it into a fraction, and see how Desmos automatically reduced it for me. But look at what the decimal is. 0.1627272727, exactly the number we started with. And so we have now shown that all of these repeating decimals are actually rational numbers because we were able to turn them into fractions that are integers over integers. All right, that was, to me, the most fun part of the lesson. Now we're just going to tie up a couple loose ends real quick. So this last part will go real quick and won't be so bad at all. The different number sets we have build on each other. Where we start with natural numbers, these are normally called the counting numbers, and we call them that because we use it to count things. So they start at the number 1, and then they go up all the way to infinity. So it's 1, 2, 3, and then dot, 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 all the way up to infinity. And this is denoted with a capital N. And again, I want to remind you that in most math notation, we use a fancier N than this, but capital N is good enough for our purposes. Whole numbers are this exact same group, except we include 0. So it's 0, 1, 2, 3, and then all the way up. And this is a capital W as its symbol. Integers are whole numbers, but both positive and negative. So dot, 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 -3, -2, -1, 0, 1, 2, 3, and then all the way up. And now this one might surprise you, but this is actually a Z, represents the integers. Okay, then we have rational numbers, which we've already seen a bunch of examples of, and we know that that is the capital Q. We have irrational numbers, which are the non-terminating, non-repeating decimals. Those are capital I. And then we have real numbers, which are all of the rational and irrational numbers put together. And this is a capital R. Okay, so now real numbers are every number that you can think of. Okay, we also have imaginary numbers that we're not going to talk about here in this class, but real numbers are literally any number you can think of. So give me any number with a decimal point, any fraction, anything that does not have the letter I in it is going to be a real number. And those will fall into one of two camps, either rational or irrational. So you can see this box below, the real numbers are divided into two groups: rational numbers on the left, irrational numbers on the right. The only types of things that go in the irrational box are things that are special and do not repeat or terminate as decimals. So we've seen pi, we've seen Euler's number, and we've seen various non-perfect roots. Okay, essentially, irrational numbers are those non-perfect roots. But on the other side of things, we have all these different subcategories of rational numbers where we know the natural numbers are the 1, 2, 3, 4, all the way up. But then we're just adding more numbers when we get into a bigger group. So whole numbers include the natural numbers, but they also add the number 0 to it. Integers then just also add in the negative numbers. So -4, -3, -2, -1. Okay, we're just tacking those on top. And then rational numbers are all of those ones. So it's the natural, whole, and integers. But then we also throw in all the fractions that are not whole numbers. So like 1/3 or -4/3, or also perfect roots that actually turn back into integers, right? But we might have fractions with roots. So we might have square root of 4/3, which is really just 2/3 is an irrational number. Okay, so rational numbers catch everything that the integers miss, essentially. But then anything that doesn't fit a rational number description goes on the other side into the irrational numbers. So now all we're going to do for these last couple ones is state all of the number sets that each value belongs to, and then determine what the smallest one is. And we're just going to do this using the symbols. So -3, we know -3 is a integer because it's negative. It is not a natural number or a whole number because it's not positive or 0. So z, which is the integers, is the smallest set that this is contained in. But that also automatically makes it a rational number and a real number. But then we're going to circle z because that is the smallest set, which is the integers. The number 0 for number 12 is a whole number, which makes it automatically an integer, which makes it automatically a rational number, and that makes it automatically a real number. So it's all of those sets, but whole numbers are the smallest. Number 13, we have 12.75. That is not an integer, but it is terminating. And so this is going to be a rational number, which makes it automatically a real number, but the smaller of those is the rational. 14 is 0.81 with a bar over the 81. That is also a rational number because it repeats, which makes it a real number, but rational is the smallest. Number 15, you might think that it's an irrational number because it has a square root on it, but square root 121 is actually just 11. So this is way more than you probably thought it was at first. 11 is a natural number, which makes it a whole number, which makes it an integer, which makes it rational, which makes it real. So it is all of them, which means natural is the smallest group it fits in. And the last one there, 16 is pi. Pi is an irrational number, which does still make it a real number, but irrational is going to be the smallest group that one fits in. All right, a couple true false for us to wrap this up, make sure we're understanding. So it says state true or false for each of these. Number 17, every fraction is a rational number. Now, we know that rational numbers can be represented as fractions, but this is actually going to be false. Not every fraction is a rational number. So as an example, square root of 2 over 1 is just square root of 2, right? Because the over 1 doesn't do anything, but that shows you it's a fraction. And that is not a rational number. That is irrational. 18, every natural number is a whole number. This is true. Every natural number we can see up there fits inside of the whole number box. Okay, so natural numbers are by default whole numbers. The reason number 17 was false is that fraction, notice, is not one of our categories up here. Okay, so fractions could fall on either side, irrational or rational. And so I came up with square root 2 over 1 is a fraction that is not rational. But for 18, the natural numbers fit entirely inside of the whole numbers, and so that is true. Number 19, every integer is a rational number. This is true because name me any integer, such as 3, and all I have to do is write over 1, and that shows you that it fits the definition of a rational number. Alternatively, you can see that again in our chart, the integers fit entirely inside of the rational numbers box. But it's because every integer can just be written over 1, and it meets that description of being a rational number. All right, and then last one, every rational number is an integer. This is just false. We can see in our chart that the rational numbers take up more space than the integers. And so there are plenty of rational numbers that are not integers, such as 1/3 is rational, but not an integer. And so that one is just completely false. All right, I hope you guys had as much fun with this one as I did. Truly, I think that if you can get down, turning repeating decimals into fractions, you now know a thing that a very small percentage of the population knows. And I think it's a pretty useful skill. I don't know if in real life it's going to help you that much, but throughout mathematics classes and just general understanding, I think that procedure of having to solve in such a fun way, it really is good for your brain, in my opinion. But all right, enough ranting about cool math stuff. I hope you guys enjoyed this one, and I will see you on the next one.